In this video we're going to look at two different approaches to calculus. The calculus we're interested in is the differential calculus, and differential calculus is that branch of calculus which is concerned with finding the rate at which quantities change. For example, suppose we have a function y equals f of x, then what we're interested in doing is finding the derivative of y with respect to x, which determines the slope of the function at a point. And we can think of the derivative as essentially determining the slope of a tangent to the function at a particular point. Now, to understand this, let's first of all look at some diagrams. First of all, it's very easy to determine the slope between 2 points on a function. Here we've drawn the function of y equals x squared. Now suppose we want to find the slope at the point x equals 5. Now we can take 2 points equally distant on either side of 5, 2 and 8, and it's very easy to determine the slope between those 2 points. We've drawn it here on the diagram where we've got delta y is the vertical distance between those 2 points and delta x is the horizontal distance. And if we work that out, we find that the value of the function when x is 2 is 4, the value when x is 8 is equal to 64, and therefore the slope of the straight line between those 2 points is given by 60 divided by 6, or 10. We can view that as an approximation of the slope at the point x equals 5. But it won't necessarily give us exactly the right answer. What we're really interested in doing is finding the slope of a tangent, i.e. a straight line which just touches the function at that point x equals 5. Now, taking a wide distance between the points like we have done may not be the best strategy. Instead, if we take a very small distance between those 2 points, then the function essentially flattens out around that value. We can see this here where we've drawn the function y equals x squared, and then we've magnified it here to show that around that point, with very small distances around that point, the function is approximately linear. And therefore we could use a linear approximation. We could work out delta y over delta x, and hopefully that would give us a good estimate of the slope. The problem, of course, is what constitutes a small interval around that point. And here there are two possible approaches. The one commonly used in the textbooks is the approach of limits, and that was developed by Weierstrass in the 19th century. And basically the idea is we take a small increment in x, h, and then we ask the question, what happens to f of x plus h minus f of x divided by h as the value of h gets close to 0? And that's the approach that dominates most of the textbooks. But there is another approach which I think offers some advantages, and that's the approach of non-standard analysis. Now, with non-standard analysis, what we do is we define the derivative as dy dx as the standard part of f of x plus delta x minus f of x over delta x, where delta x is an infinitesimal change in the x variable. It's a very, very small change. And in non-standard analysis, the concept of an infinitesimal has got a very precise mathematical definition. In fact, non-standard analysis was developed in the 1960s, and it's a branch of mathematics which deals with numbers like this, which are either infinitely large or infinitesimally small. And it was developed by Abraham Robinson as a way of making the calculus of Leibniz mathematically rigorous. Because what had happened is that mathematicians had essentially rejected the original derivation of calculus through Newton and Leibniz in terms of infinitesimals in favour of the limits approach that was developed by Weierstrass. Now, it's my view that non-standard analysis offers a more intuitive approach than the limits approach. Although the limits approach is undoubtedly the more commonly used approach in developing calculus in textbooks. So what we're going to do is we're going to take a look at each of these approaches and see how we'd use them to determine the slope of the tangent of the function that we've been looking at. Suppose, for example, we want to use the limits approach to find the derivative of x squared. So this is our function y equals x squared, and we define the derivative to be the limit as h tends to 0 of x plus h squared minus x squared over h. So if we expand out that top line, we can write it in this form. So we're taking the limit as h tends to 0 of x squared plus 2xh plus h squared minus x squared over h. Now obviously we can just eliminate the x squared from the numerator of that expression, and we can write it as the limit as h tends to 0 of 2xh plus h squared over h, and dividing through by h, we can write that as the limit as h tends to 0 of 2x plus h, and as h tends to 0 the h term will disappear and we'll be left with 2x. And that's fine, that's the way that most textbooks do it, and it works very well. However, with some of the more complicated derivatives that we need to find, it becomes increasingly hard to use this approach. So an alternative approach is to use non-standard analysis, where we take infinitesimally small changes in x and then use this to find the derivative. So for example, again, let's assume we want to find the derivative of x squared. We take a small change in x, delta x, and that produces a small change in y as shown by this equation here. So we've got y plus delta y equals x plus delta x all squared. Now if we multiply out that bracket, we can write that as y plus delta y equals x squared plus 2x delta x plus delta x all squared. And of course we can again subtract y and x squared from both sides, and we'll be left with delta y equals 2x delta x plus delta x all squared. Now, if we divide through by delta x, then we get an estimate of the slope. Delta y over delta x equals 2x plus delta x. This is not yet the derivative. The derivative is defined as the standard part of this expression, or the non-infinitesimal part. So if we take the standard part here, we get dy dx equals the standard part of delta y over delta x equals 2x. Now notice that both these approaches have given us the same answer. In both cases we've got dy dx equals 2x. So if we wanted to work out the value of the slope at x equals 5, we get a value 10 in both cases. However, both these approaches have got advantages and to some extent disadvantages. These won't become apparent until we've considered some more complicated examples. But for the moment, what we've done is establish that we can use both these approaches to determine derivatives.